the plant discharge effluent to a river or whatever, and temperature initial is T equals 45 degrees C, you have the river flow at this velocity, and basically here is the whatever the equation name it is for the heat transfer, and you got alpha here and K value here. The first question asks you to simplify the equation by changing this to a simplified form. And the first thing is to consider about the whole scale of the problem. Basically, because we have u in y and z. So this is x direction, and whatever the y and z direction is, we don't really care about them because here we have all the velocity comes to 0. So in this way, and it asks you to derive back here. So in this way, it will become partial t over partial t plus here because only u left, so it's u times partial t over partial x. And then you come to here where, because the alpha here is relatively small, if you analyze this in a dimensionless way, as suggested by Budi here. So what he got here is alpha over UL. And basically this is the way when we are analyzing the relative importance of a parameter. As you can see, we have PE, 3 numbers, PE, PR, and RE. But here we are considering about alpha, so not RE related, and we are considering about the mass transport or the diffusivity versus inertial force. So we just use the proper number, proper form for either P or PR. I can't remember. Check for yourself. And then basically what you get is this number is really small. So basically here you got alpha 10 to the power -7. U is about 1, and L could be very large because it's a river or something. So basically you just cancel this 4, and what left here is minus K times T minus T river. So what this means is as we just saw at certain point where at certain point we consider the problem where we say here we consider this point T equals to 0, and what we want to say is when the flow here is mixed, and it flows. When it flows, how the temperature changes relatively to the river. In this case, we'll define a new variable called theta, where theta equals T minus TR to simplify our work. So here we get this, and we further simplify this because partial t over partial t. If you consider partial theta over partial t equals partial t minus t river over partial t, because here t river is a constant, and when you are doing the differentiate, it disappears. So basically, partial t over partial t equals to partial theta over partial t. In that way, this term becomes partial theta over partial t plus, here we can still say in a similar way, partial theta over partial x equals to k times theta. And we put this term into this side, get the value here. So this is what was the result from the first analysis. So here's the answer for question 1. Simplify it to this type of form. And then, because let me see. Let me see.
Don't worry.
I'm worrying. Because k here changes. Why does it change?
Something we didn't know.
That's fine, I think. Yeah, don't worry too much about it. Even he said k equals to small k times L over U. We didn't really use this thing, so basically just take k equals to the value of k given here. This is what he used. Don't worry about that.
Okay.
I think that's kind of mistakes because when you're scaling this, I don't think he scaled it properly.
That's out to him.
And then we need to solve the boundary conditions for this equation. Before we do the boundary conditions, let's further simplify it because here we got equation is a PDE, partial differential equation with both t term and x term, and it's really hard for us to differentiate like this. So we apply another scale that initially it looks more difficult, but then it simplifies the equation. So we introduce another parameter called, let's see what he used here. He used s, so we have a s, where s is also a function of x and t. So f is something similar to your reference temperature difference. It also changes with time and distance as you go through. And because f is what we define, so we can define it, and so that partial theta over partial s because s is a function of x and t. So partial theta over partial x times partial x over partial s plus partial theta over partial t times partial t over partial s. This is the chain rule, where if you have a function of two parameters, you differentiate in for both terms. In that way, we get two equations here. So let's say, in that way, we get partial theta and partial t, and partial theta over partial x and partial theta over partial x. So we can define, because still we are defining function s, this is how we define it. We define s as the property, so that partial x over partial s equals to u, and partial t over partial s equals to 1. That's how we define it. So we get an equation which is s is a function of both x and t, and we define it to be partial x over partial s is u, and partial t over partial s is 1. This process tells us how to define s for the simplicity of our equation. And in that way, we can say this whole term here, it becomes to partial theta over partial t times 1, which is here. So, and plus partial theta over partial x times u, which is partial x over partial s. So the whole thing here becomes to partial theta over partial s. And we get an equation of s. Everybody's clear now. Yeah.
Excuse me.
Yeah.
Here is k theta. I mean,
So we didn't move anything around k theta.
okay.
Initially, when we finished part 1, we got the equation as partial theta over partial t plus u times partial theta over partial x plus k theta. This is what we got from question 1, and then we define the function s to make partial theta over partial x plus k theta equals 0. And then we can solve this quite easily because it is in a very simple form. But before that, let's further define the function between s and x and t. So we have let me exact partial s plus k theta equals to there. So here's a condition that we haven't used so far, and let's try to solve this, and then try to find. Let's solve s first, and then find the relation between theta and s. So s first, and we have equation for this, and if we integrate it, we have x equals to u times s plus a, for example. This is the constant you will always get when we are doing the integration. And we have t equals to s plus b. And as I said, s is a function that we define to help us solve the problem, and it's also a function of x and t. And how do we define a and b really depends on ourselves, because we define the function for here. And for the simplicity of the whole work, we just say we consider everything from this point, and we consider t is 0 at this point. So everything starts here, so b becomes to 0. So we neglect b. And we say we consider this point here is of distance a here to the initial point where the water is discharged in. Here, all the mixing takes place, and whatever how long the distance it is, when it reaches this point, is even. Everything is even. It's quite homogenized.
That means like partial y over partial v over partial y is 0. Partial u over partial y is 0.
Yeah. We only consider there's variation in this axis. We don't consider in this direction because everything is mixed and goes evenly in this way. So in that way, we can say t equals s. So what you get here, us, basically you can write in ut. That's another way to express the relationship between your x and t. And here we got the equation for s. We come to find our theta, and because here you can see partial over partial s. Now you can write just d because there's only one variable here. Equals to minus k theta. So you have 1 theta d theta equals to minus k times ds. And by solving this, you will get here is log theta equals to minus k times s plus another constant, let's call it c. And we said t equals to s, so what you can substitute here by t. And then you will get equation which is theta equals to e to the power of minus kt plus c. And basically here, you can put it at the front. You get this value. So that's how you solve it. But the question is almost solved. What we like to do is to find a, and we have a boundary condition where we haven't used is t not equals to 45 degrees C. So just pop that in, and we will get anti-river is 20 degrees C or something, I think. Theta we said is t minus tr, and at very initial, it becomes to 25 degrees C. So 25 degrees C equals to a times e to the minus k times, we said is the initial condition, so here is 0. So basically equals a, and then we solve a. So the whole problem is solved. It's done.
Do you know how this was wrote?
Oh, d.
Yeah.
Tr equals to 25, right?
20 or 25, I can't remember. I think it's stated in the problem.
And theta equals to t minus tr.
Yeah.
And in the initial condition,
Yeah.
or theta like t equals to initial condition, the temperature is how much?
Initial temperature is stated here is 45 degrees C.
Okay. So theta is.
I can't remember what exact the river temperature, but it doesn't affect too much. And then Budi said the question here is wrong. It's not cool down to the normal stream temperature, because basically what you will get is theta. Let's just call theta naught, which is our A at initial conditions, with E2 minus K and T. If you plot for this, you will get something like this. Well, probably like this, because here is a decaying exponential form. And basically, if you want to reach a certain point, and it won't reach unless t equals to infinity. So basically, it will never reach the normal steady state. The thing is, you can just say how much you would like it to fall down to. For example, if it falls down to 90% of its original, then this becomes to 90%, then here is becomes to 0.1 theta naught equals to theta naught times minus k times t, and you can solve t easily. Yeah, and if you want to find the length here, if you know t, substitute it back. We know u, we know t, and a is what we define. Budi here define it to be 20 meters. You can define whatever reasonable number you think for the river to make a homogeneous.
So it's ourselves that define the value of A.
Yeah. You just give it a reasonable guess. Well, I think 20 meters is enough for water to mix. That's fine. Yeah. And basically, that's how you solve it. To summarize, the idea is first to simplify the equation to get a reasonable, easy form to deduce. And for this one, you then deduce this one. We here introduce a new variable theta, and then we introduce a new variable of s. But then we found s in relationship with t and x, and then we found the relationship between s and theta, and we solve theta. That's it. Yeah.
Let me see. This is theta.
You see that equation there which says ln theta equals
Yeah.
minus kt plus e. Why was the equation before ln?
Because this is how you do the integration for 1 over something. So if
Oh yeah,
Yeah,
of
you
course.
have
Yeah,
minus theta.
sorry, yeah, of course it is, yeah.
yeah.
I'm doing silly.
That means okay.
Yeah, that's just been integrated from both sides.